Welcome friends, welcome to another video of TG Chemistry on the topic of supramolecular chemistry. So basically this is the second lecture on this supramolecular chemistry topic, and today I will talk about host-guest chemistry. And as I said in earlier class or the introduction of supramolecular chemistry class, that the supramolecular chemistry is the discipline which covers the chemistry of molecular assemblies and of the intermolecular bonds, and usually deals with the organized entities that result from the association of two or more chemical species which are held together by intermolecular forces. So, and also I have mentioned in the earlier lecture that the two major portions in which the supramolecular chemistry can be divided, one of them is the host-guest chemistry. So today basically I will focus on this host-guest chemistry. So let's see. First, this slide I have shared earlier as well, where I have compared the molecules with the supramolecular assemblies. And again, starting the host-guest chemistry, this is also very important to talk about this again, where you can see in the molecular precursors here, here you can see with these molecular precursors, they can combine with each other by means of covalent bonding, and these are known as the molecular chemistry. Okay, so these are the molecular chemistry. And in covalent molecules, the features which we study usually are the chemical nature of the covalent molecule, the shape, redox properties, the homo-lumo gap, polarity, vibration, rotation, magnetism, chirality, and few more. When such compounds which are able to function as guest and host molecules, which in turn prepared by means on this covalent bond chemistry, that means in terms of the molecular chemistry, when they combine with each other by means of intermolecular forces, not covalent bonding, they form or they create the supramolecular chemistry. And more often and in most cases we found some other functions or properties which were absent in covalent bond chemistry. Such specific characteristic function or properties will involve the recognition, catalysis, and transport properties. Okay, and the general basic features of supramolecular complexes involves the degree of order, the interactions between the subunits, symmetry of packing, and also the intermolecular interactions. So these are basic or general features that are usually absent in covalent molecules. Okay, and by means of supramolecular chemistry we can access those properties or such new properties, rather say, which are absent when host and guest molecules are not combined together to form the supramolecular complex. So this is the beauty of supramolecular assemblies. And with this brief introduction, I will move to the next part of the supramolecular chemistry. In the host-guest chemistry, it can be said that it involves the design, synthesis, and investigation of simpler organic compounds that imitate working features of naturally occurring compounds. The four basic features of host-guest chemistry that has been studied or that are very mostly useful in the reactions are the molecular recognition, transport phenomena, regulation, and catalysis. So here in this lecture I will talk briefly about the molecular recognition part. A molecular recognition process can be described as a specific interaction between two molecules through multiple non-covalent contacts. Okay, so the molecular recognition forms can make the basis of many processes in the biological systems. Some of them are like receptor substrate binding. It can be the enzyme catalysis, which was proposed at the very beginning by Emil Fischer in terms of the lock-key principle. I will come into that in next slides. Assembly of multi-protein complexes, and active and passive ion transport across the membranes via ion pumps, ionophores, and channels. I will talk about this one in very soon. So then few definitions need to be known as keywords, like the host. What is commonly known as host? It is the organic molecule which contains convergent binding sites, synthetic counterparts to receptor sites in enzymes, genes, antibodies, or ionophores, depending on the phenomena that we are considering. Guest molecules or ions contain the divergent binding sites and the counterparts to the substrates, inhibitors, cofactors, and antigens. Okay, so these are generally the guest molecules. And what about the complexes? The host and guests held together in solution in definable structural relationship by electrostatic forces, which are generally the enthalpic component, such as the ion pairing, hydrogen bonding, or the metal ion to ligand interaction, the pi-pi stacking, dipole-dipole interaction, van der Waals interactions, and also the entropic component of the desolvation. Here in the graphical picture, you can see that the host molecules in terms of with the greenish color, and with the off-white color the guest molecules, and the component can combine together to form by means of non-covalent interaction at the binding sites, which are shown here by D1, D2, D3, and A1, A2, A3, and they form the complexes of consideration. So these are basically the host guest interactions and the basic key words which and their meaning which need to be known when we proceed further. Then comes the examples of synthetic host types, not the natural one. These are the synthetic ones that are prepared in the laboratories, and the first one which comes under that is the macrocyclic host molecules, and it contains the CrownEthers and cryptons. The cryptons are basically the family of synthetic bicyclic and polycyclic multidentate ligands, and they are very useful for various cations. The term crypton implies that this ligand binds with the substrate in a crypt, entering the guest as in a burial. Okay, so that's why the term came from there, and it is these kind of molecules are known as crypton. And these molecules are three-dimensional analogs of CrownEthers, as you can see in the picture here, that these are the CrownEthers. If you can see, these are the CrownEther molecule, and this is the crypton molecule, the three-dimensional versions. And these I mean, they are the three-dimensional analog of CrownEthers, but they are more selective and strong as complexes for the guest ions. Okay, and the resulting complex with the guest ions are lipophilic in nature for cryptons. Okay, I will come or I will talk about the CrownEther in the next slide, and but let me finish the other parts. Like then comes the molecular clefts. You can have a representational structure, how it works, and if we say that the molecular clefts are basically the rigid receptors which exhibits the convergent functional groups which are directed toward each other and separated by a spacer. Okay, and the spatial disposition of the functional groups that defines a space where a guest can fit into actually. Okay, so like the examples here, you can see here the example as the molecular tweezers. So these are very well-known examples for that, and these molecular tweezers are the supramolecular, nothing but the supramolecular host molecules equipped with two aromatic pincers linked together by a spacer. Okay, and they are generally endowed with the fascinating properties originating from their ability to hold the guest between their aromatic pincers. And the open cavity of the molecular tweezers that may bind with the guest using the non-covalent bonding, which includes as we talked about that can be the hydrogen bonding, the metal coordination, the hydrophobic forces, van der Waals interactions or forces, the pi-pi interactions, and also it can be the electrostatic effects as well. So these are with the molecular clefts, and especially in terms of the molecular tweezers. Then comes another interesting host type which falls under the type of bowls, and these are cavitants. Okay, and another one is calixarine. So the cavitants, if we talk about the cavitants, it seems that these are kind of container kind of shaped molecule, and the cavity of the cavitant, it allows to engage in host guest chemistry with the guest molecules of and definitely that has to be of complementary shape and size, then only it can fit with the container or the cavitant shape. And the original definition was for the cavitant was proposed by Cram. It can be the cyclodextrins or calixarins. Those kind of molecules fall under this category. Okay, so these are another beautiful host type, synthetic host type in the host guest chemistry. Now the calixarin is a macrocyclic or cyclic oligomer based on a hydroxyalkylation product of phenol and an aldehyde. Generally they are like that way, and they can form a circular structure by which within which or in which the guest molecule can come and fit in accordingly. Apart from these three, it can be also the linear type of host molecules, for example here with the saturated atoms and with even with the aromatic backbone, by which can interact with the linear guest molecules as well by means of hydrogen bondings, as you can see over here. Okay, so these are another type of synthetic host molecules. So next we will talk about the complementarity, which is very important when we are talking about the host guest chemistry, that no steric clash or constraints, and there should be no steric clash or constraint for a good fit with respect to the size and geometry of the host and the guest both. The interactions are available between the host and the guest and are well aligned in the complex. And what kind of interactions it can be? It can be the hydrogen acceptor and donor pairs, the Lewis acid and base pairs, the complementary charge distribution, and some others. Okay, but what we need to keep in mind that most molecules are not that very rigid, and therefore they give the options of they give the option for the next steps like induced fit. I will come into that. So coming into this lock and key model, it is also called the Fisher's theory of one of two models, in which it describes the enzyme substrate interaction. The lock and key model actually assumes that the active site of the enzyme, here you can see that in terms of the lock and key model, that the active site of the enzyme and the substrate are equal shaped. Okay, so they fit with each other in terms of the molecular shapes, and then it can act as a lock and key, and it supports is supposed that the substrate fits perfectly into the active site of the enzyme and makes the enzyme highly specific, and in that case each type of enzyme can catalyze only one type of reaction or only very few type of reactions, you can say that. And if the shape of the enzyme changes, its active site may no longer work because it will not fit into the shape of the enzyme. Okay, so this is for the lock and key model. You cannot manipulate the shape of the enzyme and the substrate. It has to fit accurately with each other. Another version is the induced fit. It gives some flexibility. Okay, some conformationally flexible host or receptor can form the induced fit, the mechanism. Okay, and this induced fit model states that a substrate binds to an active site and both change the shape slightly, creating an ideal fit for catalysis, the host and the guest, both of them. When an enzyme binds its substrate, it forms an enzyme substrate complex first, that we know, and then the enzyme will allow always to return to its original state as at the completion of the reaction. Okay, and induced fit indicates that a continuous change in the conformation or the shape of an enzyme in response to the substrate binding, and this makes the enzyme catalytic, which results in lowering the activation energy barrier, causing the increase in the overall rate of the reaction. Okay, so this is the backside story for that. So this is about the induced fit. These are very two important topics, the lock and key principle and the induced fit mechanism. Uh, if the shape of substrate and size, I repeat it again, are rigid and they are fitting with each other, then the binding will be possible. And if any one of them changes the shape and size, then the lock and key principle will not be there. So no binding will be there unless the excellent geometrical complementarity is again achieved. In case of induced fit, this gives some flexibility in the host-guest receptor interactions. Okay, so these are the two very well-known principle and two important principle when we are studying the host-guest chemistry. Next come the CrownEther complexes, very interesting one. Here, first thing that we need to remember is the high complementarity often result in high affinity. These are very important. Here you can see the three macrocyclic structure over here. This one is called the 12 crown 4. This is the 15 crown 5. This is the 18 crown 6 ethers. All these are ethereal macrocycle. Okay, and we know that the 18 crown 6 is having the binding selectivity with K plus, whose size matches with the cavity of the 18 crown 6 in a very fitting way. And the cavity is polar inevitably in presence of the oxygen atoms surrounding that the cavity, and outside complex is lipophilic. Okay, and the complex is soluble in very nonpolar solvents like benzene, and in nonpolar solvent the counter anion X minus is not solvated, so this remains as the naked ion. This is very important one. So this one remains as the naked ion. So this is very nucleophilic and reactive in nature because it's moving freely inside the reaction. I mean in the mixture. I mean, for example, in water, if the solvent is water, then the nucleophilicity of will be in the order of I minus, greater than Br minus, Cl minus, and much greater than the fluoride. In benzene, it should be the naked ion. The nucleophilicity or reactivity should be the other way around, that F minus will be greater than Cl minus and Br minus. So it depends on the solvent. If the solvent is non-polar solvent, then the counter anion with the K plus, here with the K plus, if we talk about the K plus, if the salt was KCl or KF or KBr, so the counter anion F minus, Cl minus, Br minus will be the non-solvated and move around as the naked anion. Okay, so this is an interesting phenomena or property of the CrownEther complexes. And for the CrownEther, the solvation energy increases, as you can see, in terms of the ions, that K plus will have the less energy than Na plus and Li plus, and therefore K plus fits in very well with the 18 crown 6 ether molecule. And so from there we can say that the CrownEthers are not completely rigid, because we couple of slides back we have talked about the cryptands, which are the three-dimensional, a little bit more rigid version of the CrownEthers. So CrownEthers are not that rigid compared to the cryptands or so. So here we will talk about one thing, as I said, that the passive transport, passive ion transport. Here you can see over here that this passive ion transport across the biological membranes, this is defined as the movement of a solute from a region of high electrochemical potential on one side of the cell membrane to a region of lower electrochemical potential on the opposite side. Okay, the sodium potassium pump moves the potassium ion into the cell while moving the sodium ion at a ratio of 3 sodium ion for every 2 potassium ions. Okay, so when the sodium potassium ATPase enzyme points into the cell, then it has a high affinity for the sodium ions and binds 3 of them, hydrolyzing the ATP and changing the shape. And here ionophore and the ion channels play an important role for the transportation of the ions across the biological membranes. So these are another important phenomena where supramolecular chemistry plays a very important role or is involved actually. So then we will talk about a very interesting phenomena. This is the cyclodextrins, and these are a family of cyclic oligosaccharides consisting of a macrocyclic ring of glucose subunits which are joined by alpha 1,4 glycosidic bonds. And these are composed of 5 or more alpha D glucopyranoside units which are linked from 1 to 4 as in amylose, which is a fragment in turn of the starch molecule. The typical cyclodextrins contain a number of glucose monomers ranging from 6 to 8 units in a ring, creating a cone shape. And for alpha cyclodextrin, there should be the 6 glucose subunits, and for beta cyclodextrin, it should be the 7, and the gamma, it should be the 8 subunits will be there. Okay, so we will see the structures here now. So these are the structures of cyclic oligosaccharides composed of the D-glucose units and connected via the alpha 1,4 glycosidic bonds, as I have said. Here you need to understand that with by means of alpha cyclodextrin, beta and gamma, the macrocycle, the groove inside the macrocycle increases gradually if we go from alpha, beta to gamma, and their water solubility also changes. You see, for the alpha cyclodextrin, the solubility is 145 gram per liter. It comes reduced to, for the beta one, with the 18.5, whereas in gamma cyclodextrin it is around 232 gram per liter. Okay, and the cavity size and the cavity diameter, this also changes ongoing from the alpha to gamma cyclodextrin. In addition to that, the cyclodextrins have been applied for the delivery of a variety of drugs, including the hydrocortisone, the prostaglandin, the nitroglycerin, and chloramphenicol as well. So these are very well-known drug molecules, and cyclodextrins are applied for the delivery of such drugs. They confer a solubility and stability to these drugs, and thereby the inclusion compounds of the cyclodextrins with the hydrophobic molecule are able to penetrate the body tissues. This can be used, therefore, for the to release the biologically active compound which can be generated from the drug molecule under specific conditions. And in most cases, the mechanism of controlled degradation of such complexes is based on the pH change of the water solution, leading to the loss of the hydrogen or ionic bonds between the host and the guest molecules. Okay, and therefore these cyclodextrin molecules are so very important that they are shown to enhance the mucosal penetration of the drugs as well. So here we will see that that while talking about the binding properties of the beta cyclodextrin, we see that with the binding with the 2-methyl cyclohexanone, it shows the inclusion complex, where you can see in the groove or in the cavity the 2-methyl cyclohexanone how it fits in. Okay, and here these are the space filling models of the beta cyclodextrin and the inclusion complex. This is for the space filling model of the gas. This is the top view. This is the upper one is the side view, and this is the top view of the inclusion complex, where in the middle here, this part in the middle, these are the 2-methyl cyclohexanone which can fit in actually with the cavity of the beta cyclodextrin molecule. And coming here with the in the drug molecules, I have said some drugs already. In addition to them, the nicorette and the Voltaren, cetirizine, those are drug molecules which combined with the beta cyclodextrin, with the gamma cyclodextrin, here the beta cyclodextrin as well, and this is also beta cyclodextrin which binds with the prostaglandin. Okay, so with the diclofenac sodium salt as well, with the nicotine, the beta cyclodextrin binds with these drug molecules and deliver them to the actual part of action inside the body. Okay, so from there we can say that the better solubility and stability and result in fewer side effects as compared to the non-complex drugs. So cyclodextrin can impart such a huge role in drug delivery. So these are so far for today's lecture. Next lecture I will bring some more about the self-assembly or the non-covalent interactions, And few more things that need to be learned about the host guest chemistry is the experimental techniques. These are very important. Hope you know these techniques, like the nuclear magnetic resonance. This is the one of the most powerful spectroscopic techniques in analytical chemistry to analyze the organic compounds or any other compounds, and it is an important tool for studies the host guest complexes as well. Why? To elucidate the structures of the various complexes existing in the form of aggregates. So to analyze them, we need to have NMR data and the ion pair or encapsulated system, wherever be they. So to find that aggregate or segregation, we need to have the NMR data of the host guest complex. Another technique is the ultraviolet and visible spectroscopy, which is one of the oldest and quickest method for studying the binding activity of various molecules. The absorption of ultraviolet light takes place at a time scale of picoseconds, so you can understand how quickly they happen, and hence the individual signals from the species can be observed. At the same time, the intensity of absorption directly correlates with the concentration of the species, which enables easy calculation of the association constant. The other one is the isothermal titration calorimetry technique, and it gives information about the binding constant for the host guest chemistry, which is represented at Ka as Ka in most cases, and also the Gibbs free energy delta G. So to get the complete set of thermodynamic parameters, the Van 't Hoff analysis using the Van 't Hoff equation would be required, and from there we can have the Ka and delta G values, which are very important to predict the host guest interactions and complexation reactions. So thank you viewers for watching TG Chemistry, and keep watching my channel TG Chemistry, and if you like the videos, don't forget to subscribe my channel and press the bell icon to get notification for further videos on this topic and other topics, in important topics in chemistry, whenever I upload them. Thank you.